I'll just switch from here.
The Zoom technology, we forgot all the old stuff.
Ah, wait, I think I know what's happening. Yeah, of course, this is the part of the pressure process because we don't know how to give talks live anymore. I'm used to talking to the screen all the time.
It's colliding.
Ah, here we go.
Hamza, I'm trying to mute you all the time.
Yeah. Okay, so let's just talk a bit about what light is. So, we all know that generally light classically is described by classical electromagnetic theory. And there are many different flavors of light that we're used to seeing every day. For example, thermal light from the sun, from lamps, and so on. Also coherent light, lasers, and so on. And these can be described classically. The main difference, of course, between coherent light and thermal light, as we know, is coherent light is a coherent mixture of waves, whereas thermal light is completely incoherent. But another interesting way of looking at this is by looking at the autocorrelation of the intensity of a beam with itself in a delayed manner. So if we look at the intensity and a delayed version of it, and we do this autocorrelation, we get this second order correlation function. And second order is because, of course, we're doing it in intensity, not in the field itself. And what's interesting is for coherent beams, the G2 is at 0 delay is always 1, whereas for thermal beams, it's 2. But more interestingly, for all classical light sources, the G2 is always greater than 1, or at least greater 1 or equal to 1. Here comes in the quantum nature of light. So for now, for the purposes of this presentation, I'm taking a very simple quantum source, monochromatic, single mode light source. And I'm writing it as a decomposition of different Fock states. So there's special cases of such a quantum light source. For example, a Fock state would have exactly n photons in the field, no more, no less. And we can show that the G2 at 0 delay for this function is 1 minus 1 over n. Already you can see the nature of this. This is already less than 1, which tells you something about the quantumness of the source. An extreme version of this is the single photon source, where you have exactly only 1 photon in the field, and then this gives you a G2 of exactly 0. So generally speaking, the fact that the G2 goes below 1 is an indication of the quantum nature of the source that you have. But going lower and lower and towards 0 gives you a better idea about how pure the source is, how exactly, if you have exactly 1 photon or more than 1 photon in the field. So since we're already here, I thought I would talk a bit more about the measurement and how we actually measure this G2. So the way we measure it is using a Hanbury-Brown twist. We take the signal, we split it on a beam splitter and take it to 2 different detectors. And now we do an autocorrelation. We do a cross correlation between these 2 detectors. Because the source is the same, this turns out to be the same as doing an autocorrelation on the same on the source here. And then you can introduce a delay, either optically in between these 2 lines or electronically in after the detection process. But what people usually do is take these detector signals to a time tagger, which tags the arrival time of every photon at each detector, and then in a post-processing step on the data, you can do all the correlation. And this enables you to measure for all delays. Otherwise, you would have to keep on changing the delay and measuring each time. So this is an example of such a second-order correlation function. If the source is pulsed, meaning it arrives at fixed times, this is how it would look like. If it's arriving randomly at a time, this is what it would look like. This dip in the center here is an indication, again, of the quantum nature of the source. And if it goes below 0.5, it's actually considered as a single photon source. Not as such a good one, but single photon source, nonetheless. Okay, so now we know a bit about G2 functions. Now let's go to the Let's go to the real world. So all this is nice in theory. You can create a single photon, exactly single photon source, but in reality, of course, it's not so clean. First of all, most sources tend to operate very well at cryogenic temperatures. We want to try to bring this to room temperature. There's also an issue of purity. We'll be talking a lot about this in a minute. So you don't really get a source that gives you exactly 1 photon every time. There's an issue of single photon purity, and we have to fix it. there's an issue with brightness. How many photons per second can you get out of this source? Okay. And finally, there are some more practical issues, such as how scalable your technique is and how easy it is to use. So this plug and play issue. And finally, some somewhat important criterion for some application is indistinguishability. How alike are your photons to each other, the ones that are being emitted? Okay, so what can we use these sources for? Well, I think at least I know the people in the room know that how useful these are. So for example, we can think about applications such as quantum key distribution, where you have this light source, you entangle it randomly in one of two bases, send it to someone in the other side of the world. And the fact that you randomly choose the basis in which you encode the information, and the fact that it's a single photon that you're sending, means that if anyone in the middle tries to read this, it will introduce errors that can be detected by the two parties, which makes this physically secure way of exchanging information. So this is what's called quantum key distribution. There's also the whole craze these days about quantum computation. So in the photonic realm, you can imagine doing quantum computation either using linear optical quantum computation with these CNOT gates, or using these nice cluster state sources, what HUJI is doing now with Pascal, and do some post measurements on these to do quantum computation. Now, the different applications require different requirements. For example, you can see here a few such applications with what purity they require, whether or not the photons must be indistinguishable, and the efficiency and repetition rate basically are the brightness I was telling you about before. Just to give you an additional motivation, these things are already commercial. There are already companies built out of academic labs that provide people with single photon sources. So their whole business is to give you a single photon source or give you a platform to use their single photon sources. One example is this company called Quandela, built out of Pascal Sennelar's lab in Paris. Another example is Sparrow Quantum from Copenhagen, out of Paul Lodal's lab, Peter Lodal's lab, sorry. And there are already people also using these single photon sources to do stuff like quantum computation. For example, PsiQuantum are using these nonlinear single photon sources to do linear optical quantum computing. And this is a company out of Jeremy O'Brien and Terry Rudolph's labs in Bristol. So you can imagine that this is really something that's quite relevant in today's quantum world. So now I want to give you a bit of motivation why we want to do this in a solid state platform and why we want to do it at room temperature. So the fact that it's solid state enables you to make very compact sources, unlike nonlinear sources, which require much, much larger platforms. That means also you can make them scalable. And the fact that it's room temperature means that it's much less demanding on the resources to operate the source. And there's already a few sources which can operate at room temperature, such as colloidal quantum dots or defects in crystals. And we'll talk a bit more about this in a minute. But all of these face some challenges as well. And one challenge is this isotropic emission. So these emitters tend to emit in all directions, and you can only collect a finite amount of their photons given by the collection cone of your optics, so the numerical aperture of your optics. So this is one problem. The other problem is that they're typically quite slow, tens to hundreds of nanoseconds, which limits you to rates that are too low to be useful for applications. And we'll talk a bit more about this in a moment. And the final thing is that they have quite broadband emission. So first of all, that means they're incoherent, of course. They're not distinguishable, but it's more than that. This broadband emission makes it hard to put them in any structure you can imagine, okay? So this really limits the useful brightness of these sources, and they've been overlooked a lot because of all of these different shortcomings. And there's an additional problem of single photon purity we'll be talking a bit more about in a moment. My goal today is to show you that we actually we managed to overcome these problems, and we achieved very high single photon purities in the order of 99.5%, along with very high single photon rates on the order of 10 to the 8 photons per second. So this is the goal of my talk today, and I hope by the end I'll be able to convince you that I did. So let's talk a bit about the purity part. Okay, so we call this purification. Just as a side note, I've been approached sometimes talking, when I say purity, some people imagine the purity of the mode of a single photon. That's not what I mean. I mean, by purity, I mean exactly a single photon out of the source. That's what I mean. Okay, the single photon purity is what I mean when I say purity. Okay, so in order to give you a proper motivation, I want to give a concrete example. So I'll be telling you a story about these nanocrystal quantum dots. So these nanocrystal quantum dots are very nice. They consist of a core of semiconductor material encapsulated by a shell of another semiconductor material. And what's nice about them is they're relatively easy to fabricate. They're fabricated using colloidal chemistry, makes them very easy to make. Well, easy for a physicist who just buys them, but generally quite easy to make, I imagine. They operate at room temperature, which is a unique feature that it's hard to find in many sources. They have a very tunable spectrum. This is what's really amazing about these sources, is you can, by just changing the size, which has to do, as I'm told, I don't know, that it just has to do with the time they allow these quantum dots to grow. You can tune the spectrum. For example, for cadmium selenide, cadmium sulfide quantum dots, you can go from 400 nanometers all the way to 750 nanometers or something like that. So this is a very large tunable range just by changing the size of the quantum dot without even changing the material. Of course, there are many different quantum dots with different materials they use also to reach other wavelength ranges. Gotta be kidding me. This thing is inconsistent. Okay. Yeah, I'm deterministic. Okay. Do you have, where's Rossi? Yeah, so I think it's just not so good. Anyway, thanks. And because they don't require any substrates, they're built separately from the substrate you want to put them in. They're relatively easy to integrate into any structure you can imagine. Okay, so this is a wide sweeping argument, but it's kind of easy to put them where you want them to be, which is not something you can say about all of these epitaxial stuff where they have to be in the same substrate where they're built. They do have an issue with stability, but this has been solved in the recent years, and they've become quite stable. So intensity stability. So they tend to fluctuate in intensity and bleach over time, but this has been recently solved with the giant quantum dots. But the major problem is with this multi-photon emission. Okay. So this is the multi-photon emission comes from this process here that you see, mostly from this process that you see here. So you have a quantum dot that's in the ground state. No, all the electrons are here. There's nothing here. Then you excite it. Often when you excite it, especially if you excite it hard enough, you'll end up in this bi-exciton state with 2 excitations inside the quantum dot. So you have 4 charge carriers. And then this is called the bi-exciton state of the quantum dot. It can relax to the exciton state with 2 charge carriers by emitting a photon. This is, of course, indeterministic, this photon emission. It's given by the bi-exciton quantum yield. So it could happen either radiatively or non-radiatively, and the probability that it happens radiatively is given by the bi-exciton quantum yield. And now the exciton can itself relax to the ground state with another exciton quantum yield, with giving another photon with a probability of the exciton quantum yield. And this leads to this indeterministic 2-photon emission. Okay, if it was perfectly deterministic, then you have a 2-photon source, which is almost as useful as a single photon source, but it's indeterministic, so that's a problem. 2 things are worth noting here. First is when you're in the bi-exciton state, the time it takes to relax here is shorter because you have 4 different pathways that the charges can recombine at, compared to the exciton state. So the bi-exciton lifetime is shorter than the exciton lifetime. That's very important. The second important thing to notice is that the bi-exciton photon always arrives first. Okay, and then the exciton photon. So this is the cascaded nature of this emission. And we'll use this in a moment when we talk about our protocols. So the question you might ask is, how can we efficiently distill these single photons out of such a indeterministic two-photon emitter? Well, you can imagine different ways of doing this. So for example, you can say, okay, let's try to separate them spectrally or with polarization. The issue, I remind you, is that these are broadband sources. And the biexciton and exciton lines are always overlapping. So you can't really use spectral filtering. And a similar argument goes for polarization filtering. So you're left really only with this temporal filtering techniques that we'll be talking about now. So for example, one simple thing you can do is, okay, I excite my quantum dot at some time t. Let's apply a filter after this time and throw out all the photons that come before this filter, okay, in time. Because the biexciton lifetime, as I told you before, is shorter, you end up throwing most of the biexciton emission and keeping the exciton emission. Okay, that's ideally. But imagine that both processes are quite efficient. So in this extreme case, the exciton and biexciton quantum yields are 1. So you get photons from both equally. What this plot is trying to show you is that if, when I'm trying to increase the single photon purity, I have to move this filter more and more towards the right to increase this. So I throw more and more of the biexciton photons, but I'm also throwing out the exciton photons as well. And this kills the efficiency here. So you have this trade-off between purity and efficiency that we want to try to overcome. And this is where we come in. So we came up with several protocols that operate better, specifically in cases where the biexciton and exciton quantum yields are higher. And I'll show you one here. And this is called the active switching heralded technique. I think most of you heard about this from me before. And this says, okay, instead of throwing out the photons, let's try to use them. So let's add a switch on the signal coming from the quantum dot. This is an optical switch. This switch is nominally open to the idler port. And when a detection event happens in the idler port, it will switch to the signal port. And this, obviously, because our quantum dots mostly emit only up to 2 photons at a time, this becomes a very nice purification protocol. So if the efficiency is quite high, you can get very high purity without having to sacrifice too much of the efficiency. Now you might ask, the natural question to ask here is, okay, but this relies on 2 photon emission. So you're throwing out all of the single photon processes that are happening here. How efficient can that be? And the answer is, the answer has to be of how well it does compared to competition. So the issue is, if you look at the efficiency of this time-gated protocol I showed you before and compare it to this active switching protocol I just showed you now, and plot this as a function of these efficiencies. So the probability of getting a photon from the exciton state and the probability of getting a photon from the biexciton state, you see that actually most of this region is occupied. This color plot is just the difference between these two efficiencies. And you can see that it's more efficient above this line to use this heralded technique, which tells you something. Even when the exciton and biexciton quantum yields are low, in some cases, it's better to use this. More importantly is, you see these 1, 2, 3 data points here. These are actually measured quantum yields of these quantum dots, okay? And this already tells you that we have quantum dots with quantum yields that require you to use this if you want it to be more efficient. They require you to use this heralded technique if you want to be more efficient, okay? So we wanted to do something experimental. Unfortunately, we didn't actually implement this, but what we did is we took, instead of having this a switch here, we added a 50-50 beam splitter. And here's our idler port, here's the signal port. We take our signal port to an HBT setup to measure the purity afterwards. And so, of course, there's no switching happening here. But what we do is, when we get all these time tags from the different detectors, we can emulate a switch on the data later on. So this is the post-processing step. And this tells us exactly how a switch would act. So using this, we showed that we can increase the purity of this source, so the probability of getting a single photon, from less than 90% up to 99.5%. And these are very high purities comparable to state-of-the-art cryogenic sources, but at room temperature. Okay, so this is the main result about purity that I wanted to show. So this was the part of my talk about purification, how we purify these sources. Now I want to move on to talk about how we enhance the photon rate coming out of these sources, okay? So the brightnesses we typically require are something like 10 to the 9 photons per second. This is a very high rate. And the way we can improve the brightness of these sources, as I told you before, they have these intrinsic problems, and we can improve them in two ways. One is improve this collection efficiency. So as I said before, you have an emitter that emits in all directions. You can couple them. You can imagine coupling it to some sort of antenna that would redirect the emission into the collection cone that you're interested in. Okay? So that's one way to go. And another way to go is to play with this decay rate or the lifetime, because the lifetime is quite long. If you couple your emitter to some sort of resonator, it will induce, it might shorten the lifetime of the emitter itself. And this is called the Purcell factor. The factor by which you shorten the lifetime is called the Purcell factor when you couple your emitter to a resonator. So we need to go both ways in order to get to these high rates. Okay, we need to shorten the lifetime.
Can you say a word or two about why 10 to the 9? What's the threshold with 10 to the 9 photons? What happens then?
Okay, so this is a question from Zoom. You say,
repeat the question.
Yeah, I'm gonna repeat it. So Shlomi was asking, why 10 to the 9 photons per second? Well, the answer is that these are the rates that are required in order to compete with the different, like for QKD, there are these decoy states. And if you get to rates of 10 to the 9 photons per second, you can compete with the decoy state, the other protocols that are used. For quantum computation, there's also similar arguments. So there are different, there are different competitions on different applications, and it's really, these are typically the rates that are required to compete with this in the photonic realm. Okay. So let's talk a bit more about the decay rate enhancement. So we said we can shorten the lifetime of an emitter by putting it in a cavity, and this is called the Purcell factor. And the Purcell factor depends on the quality factor of a cavity and the mode volume of the cavity. Okay, so for those who don't know what this is, I want to just give a brief, very short and inaccurate way of describing this. So imagine you have an abstract cavity like this. The focal spot of the cavity will be something like this, and the size, the actual size in real space, is called the mode volume of this focal spot. Okay, so if you put your emitter here, this would be the mode volume of the cavity. Of course, if a cavity was perfectly reflecting and never giving you any photons, you wouldn't be using it at all because it wouldn't be useful. So some photons always leak out, and this is called the decay rate of the cavity. It's usually called kappa, and the quality factor is just 1 over this decay rate, or proportional to 1 over this decay rate. Okay. So what I'm showing you here, so this color plot is the Purcell factor in terms of the quality factor on the bottom and the mode volume here. Okay, and on the top, I just translated this quality factor to line width of the cavity as well. Okay. Another important factor you need to take into account is that directionality increases with the increased mode volume. And if you can't see this right away, the idea is that the smaller your mode size is, the more angular range it has to occupy, just due to the Fourier relation between real space and K-space. So the larger your source is, the more narrower in angular range it can occupy. So this is the inverse Fourier transform. Okay, so there are quite a few interesting ways. Oh, and on the top as well, I plot the line widths of different emitters. So this part is only the cavity. This part is the emitter. So what the line width of the emitters are. Okay, so here you have, for example, self-assembled quantum dots. These are epitaxial quantum dots that operate only at cryogenic temperatures. They have very narrow line widths. And on the left here, you have all of these room temperature sources. Yes, Chagai.
If you have a higher Q factor, you shorten the lifetime of the source, so you have an emission of more photons. On the other hand, the photon stays in the cavity for longer time. So is there an optimal Q, or what would be the optimum emission rate?
No, this takes this into account already. This Purcell factor already takes into account this what you're mentioning now. which is the lifetime of the cavity itself.
So you do improve with the ultra Q.
No, but you can only go up to a certain range, because this is, I didn't mention this, and it's a good, this is in the weak coupling regime.
It goes to infinity, you know?
Yes, so I'm answering that. So
then you get nothing else.
yeah, so this is the point. This is in the weak coupling regime. And if you go beyond some Q, you go into the strong coupling regime, and you no longer can separate the emitter and the cavity as separate entities anymore. And you have to consider them together, and you're completely right. In that regime, this fails, but we're not there. We're not in that regime, and we're talking about weak coupling here. Okay? Excellent question. Oh, for those on Zoom, the question was, if you increase quality factor, arbitrarily, eventually the photons will get stuck into the cavity, and the lifetime cannot be very short, right? So, and you heard my answer. Okay. So there are many interesting regions in this plot. For example, the top right region here is typically occupied by dielectric resonators. And what's really characteristic is they have really high quality factors in large mode volumes. So these are structures like micropillar cavities or photonic crystals. And what's really nice about this is, because of the high quality factor, you can get very high per cell factors. And because of the large mode volume, you can get high directionality in the same structure, okay? However, because of the high quality factor, you have very narrow bandwidths. And this is not suitable for room temperature emitters. As you can see, if you just try to use one of these sources, you end up spectrally filtering them out, throwing out most of the photons. So usually these are limited to cryogenic operations. So they're used quite extensively for cryogenic sources, and for good reason. So for room temperature sources, we're really limited to low quality factor structures. So here you can end up with either in this bottom left corner, where the mode volume is low, such as plasmonic resonators. This is an example in the nano patch antenna, with like a mode volume of only 10 nanometers or so. Or the top left corner, where you have this very large mode volume. This is the area of typically of antennas. And the nice thing is you can get very broadband emission, which is suitable for room temperature sources, but you have to choose either a high directionality or high per cell, okay? So our solution was simply, and this is where the uniqueness of our approach goes, combine the two. Take a structure from here and combine it with a structure from here. So we have this antenna, which belongs to this region, and this nanocone resonator, which belongs to this region here. Combine them together in a single structure. What will happen is the quantum dot will couple to this resonator, the resonator will emit to the antenna, and so on and so forth. Okay? So using this is the structure that allowed us to show single photon rates approaching 10 to the 8 photons per second. So let's talk first about the antenna. And I'm glad that the pioneers of this antenna are sitting behind you there, Moshe and Nitzan. So this is called a hybrid metal dielectric bullseye antenna, which is a mouthful. The point is, it has a metal slab. On top of it, you have these circular dielectric, circular metallic rings, on top of which you have this dielectric layer. So how does this work? And you have the quantum dot in the center at some height above the metal. The way this works is, because of this dielectric, when you excite this quantum dot, it will couple preferentially to this waveguide layer here and go resonantly outwards. This is yeah. That's how useful it is. You still use it after 5-6 years of making this animation. Yeah, so the emission couples radially outwards. It encounters these rings which diffract the beam. And then we use extensive simulations to design the antenna in such a way that it will only, the diffracted beams will only interfere at angles that are normal to the surface, okay? So to show you such simulations, you can see them here. This is just the collection efficiency on the Y compared to the wavelength on the right, on the X. But this is for an antenna that's optimized for 650. So the antenna is fixed for 650. The emitter we allow to be broadband. And the point is, we want to show that collection efficiency is actually quite broadband for this source. So if you look at, for example, an NA of 0.12, which is about 12 degrees, collection cone, I think 8 degrees collection cone, you can see that it's, even at this very low collection angles, you can get very broadband emission. Of course, the larger your collection cone is, the more broadband the emission can be, because you allow larger and larger. So this is very interesting, and it gave us this hope of eventually just coupling a fiber directly to our antenna somehow, which we'll come back to at the end of the talk. So let's talk about the results finally, some experimental results. So we did this. I'm not going to talk about fabrication here, just show you the results. So on the left here, you see the antenna from the top. We're looking at it from the top. This is just a microscope image of the antenna. And on the right, this is a fluorescence image. So we're exciting it, looking at the fluorescence in space. This is just a spatial image. And the point here is to show that we actually couple this exactly in the right place with respect to the antenna. We also do this second order correlation function way back at the beginning when I started talking about this. And this tells you something about the purity of the source. So this lack of the dip in the middle tells us that the source is very, very pure. But the most critical part of this antenna, we have to show that it's actually directional. And to do that, we use a technique called Fourier plane imaging or backfocal plane imaging. Okay? So what does this technique do? Basically, you just put a lens in front of your sample. And if you go exactly one focal distance behind the lens, what happens magically, it's optics, is that beams coming from the same angle, but from different points in space, will focus to the exact same point here. Okay? What this tells us is that at this plane, the image is really an angular image and not a spatial image. It doesn't care of where the beam is coming from. It just cares at which angle it came from. Okay? So using this technique, we can actually see how the angular emission pattern looks like. And this is such an image. These are the different angles. You can see that most of the emission is coming really from the center, normal to the surface of the antenna. Okay. Now, if we and this is a real proof of the strength of our antenna in directing the emission. We can integrate this image and figure out what the collection efficiency is. So what's the probability of collecting at each angle? Here, it's just the sine of the angle. And this is the orange is the experimental curve. The purple is the simulations. And you can see that there's a quite good agreement. And for example, for an NA of 0.5, which is an NA of multimode fiber, you can get up to more than 80% of the photons already. We also compare this to different structures out there, micropillar cavities, nanowires, and so on and so forth. And the results are very comparable and even better, especially at lower NAs. But the most important point I want to emphasize here is most of these results, except this one here, and I think you recognize it, most of these results are done with cryogenic sources which have very, very narrow line widths. These results are over the full bandwidth of the quantum dot, which is about 40 nanometers. So we show that this is actually quite broadband. Like the operation is very broadband. This is the unique feature of this antenna. Just so that you don't think that this is a hero experiment, I'm showing you here 9 devices in which we measured single photons, single quantum dots in. And you can see that it's quite consistent. This is compared to what a quantum dot would look like on glass. So this black dashed line here is how it looks like on glass. Okay. So and of course, if we cut at some length, this is just showing you the different collection efficiencies from the different devices at some specific NAs. Okay, just to show you that this is really consistent over many, many devices. Another thing I want to emphasize, since we're here already, is that this this antenna is source agnostic. It doesn't care about what the source looks like. Okay. So just to emphasize that this is not just, we didn't do this only with quantum dots. We took nanodiamonds that have single NVs in them and coupled them in the same way to the antenna. And again, we showed you two functions, directionality. This is just another way of showing directionality, and good collection efficiencies. These NVs, by the way, they have spectrum ranging from 650 to 800 nanometers. So a very, very broad emission range, and yet the collection efficiencies are okay. with them. We also have some very preliminary results with silicon vacancies in nanodiamonds as well, but I'm not showing them here. I'll leave that to Boaz when he presents something. Okay, so up till now, I've shown you significant enhancement in directivity. I've told you nothing about shortening the lifetime. So what about this rate enhancement that I've been talking about since the beginning? Here is where we bring back the nanocone into the picture. So again, we fabricated this nanocone. We have a unique way of actually binding single quantum binding quantum dots selectively to the tip of the nanocone and nowhere else on the antenna. You'll see the results in a moment. So this is how the antenna looks like with a close-up. So you have this big antenna with this very small nanocone in the middle pointing outwards. And with simulations, again, we show that we can get collection efficiencies that are comparable as before, but this time with Purcell factors, with shortenings of lifetimes on the order of about 40, which is very nice. So here again are the results. So on the left, we're looking again at the antenna from the top. This is just a microscope image. And you see this little dot here. I don't know if you can see it clearly. This is the nanocone. On the right, I did something different this time. So instead of just exciting and looking at spatially, I did a confocal map. So scanning every point here, line by line, scanning the laser across to see if there are any quantum dots on the sides of this antenna. And you can see that it only emits when you're exactly at the center where the nanocone is. Okay. Again, we can do a G2 measurement, measure the G2, confirm that it's a single quantum dot. But now what's more important is that we need to show some shortening of the lifetime and that we maintain directionality of the source. So to do that, we measured the same quantum dots on glass, and we see that the lifetime is about 20 nanoseconds. And when we measure this on a device, we measure a lifetime of about 1 nanosecond. And I want to emphasize that this is we did this lifetime measurement for more than 25 devices, and they all show the same shortening in lifetime. And so this tells us that we have a Purcell factor of about 20, which is nice. And this comes along with the same kind of collection efficiency improvement that we saw before. So this is the collection efficiency from the device. Again, there are many devices. I just show you here one. And on glass, what the collection efficiency would be. So if we combine both of these factors together, the improvement in the photon rate due to the shortening of the lifetime and the improvement due to the improvement in collection efficiency, we get this brightness enhancement factor, which tells you how many more photons would you get into a given numerical aperture compared to what you would get from the same quantum dot on glass. Okay? So this is what the brightness enhancement factor looks like. You can see that at low NAs, you get these incredible factor of about 1,000 improvement in the photon rate, which is very important if you want to put these emission into a fiber, because they typically have these low NAs. But even at a moderate NA of about 0.5, you get an 80-fold increasement in the brightness enhancement. Now, we can take all of this and estimate what the photon rate is, and it turns out to be something like 10 to the 8 photons per second, which is what I told you before. Okay, so to summarize, I showed you that we are able to take these room temperature sources and overcome the different problems that they have, improve their brightness to rates of about 10 to the 8 photons per second, improve the purity to something like 99.5%. What I want to talk about until the end is this improvement in scalability and in usefulness, this plug-and-play nature of these sources. So what we want eventually is that the user will be completely doesn't know anything. It's a complete black box what's happening behind the scene, and will just take single photons out of a fiber. This is kind of what our goal is in the future. And in order to achieve that, we need three main components. The first one is we need a highly directional antenna with a single quantum emitter. This, I hope I've convinced you that we can do and can do consistently over and over. The second part is we need some sort of on-chip excitation source. And to do that, we have two approaches that we're currently following. One, which is the work Boaz is mainly doing now, is an optical excitation source. So what we do is we take this antenna, we introduce the hole in the middle, and now we can excite actually from the bottom and collect from the top. Okay? So this is very interesting. We have some very interesting initial results on, but again, I'll leave this to Boss to tell you about more in the future. Another interesting approach we're thinking about is electroluminescence. So to excite these using electroluminescence, building a single photon LED, which would be a bit difficult, but I think is also very exciting. And finally, once we manage to excite on chip, we can just directly couple to a fiber from the top. Okay, so this is the goal. And again, we imagine that we can take these sources into different applications, such as quantum key distribution, where people are actually already have been using single photon sources for these BB84 sort of protocols. Maybe also thinking about doing this in free space, not just in fibers. But there are also other applications, such as random number generation using these single photons. So there's this very interesting new work that's been on the archive this year, last year now already, with a single photon source here that is split into different channels, and based on which detector it derives on, you generate a different random number. And this is quite interesting. There's also this whole field of metrology, weak absorption measurements that you can imagine. And here, the point is that the single photon sources are really amplitude squeezed light. You can use this in different applications. For example, you can use, because of this sub-shot noise feature, you can measure sensitive samples. Or if you have a sample which has very large transmission, you can measure the transmission of the sample, or calibrate some very good detectors using these samples. So at the end, I want to thank our collaborators, without whom this work would not have been possible. So from Los Alamos, these are the people that are placing the quantum dots on these bullseye antennas, the group of Jennifer Hollingsworth. From Tübingen, we have a group of Monica Fleischer, and specifically her PhD student, Annika, who selectively bound these quantum dots to the nanocones. And of course, here locally, the group, Boaz, Ronen, thank you very much. So I'll leave you with this publication slide and just a few words of